It's a very great pleasure to welcome Michel Janssen for our colloquium. I first met Michel, I think, when he gave a talk at the APS on a manuscript written by Einstein together with his friend Besso about the advance of the perihelion of Mercury. 2 years before Einstein actually got the correct theory of general relativity, so the manuscript was based on an incorrect theory. They got the wrong answer, but the method they used was precisely what Einstein used 2 years later after he had the right theory. And he surprised Hilbert and everybody else in the world that he could so quickly do this calculation, but he'd actually already done it. Just made a small change. And unfortunately, he didn't acknowledge Besso or even have him as a co-author. Anyway, so Michel Janssen is my favorite historian of physics. He got his master's in theoretical physics at the University of Amsterdam and a PhD in history and philosophy of science at University of Pittsburgh. And he became a professor of physics at University of Minnesota in 2000, I think. He's been co-editor of the Einstein Papers project, and he was chair of the APS Forum on History and Philosophy of Physics, and he's a fellow of the APS. His concentrations of interest in history of physics have been in relativity, mostly general relativity, of which he's like one of the preeminent world experts. Recently finished a book co-authored with Jürgen Wren on how Einstein found his field equations. And but since 2006, he's also developed a deep interest in the history of quantum mechanics, for which he has a long-running collaboration with Anthony Duncan. And they've got scores of, I don't know how many papers, tons of papers they've written, but finally recently completed volume 2 of a 2-volume history of quantum mechanics called Constructing Quantum Mechanics. Volume 1 is called the Scaffold, and volume 2 is the Arch. And I'm sure we'll hear about that metaphor today. I think today's talk is about the transition from the scaffold to the arch. And I just want to thank Michel for coming and talking to us.
Well, thank you. Well, thank you all for coming. It's a great turnout, and thanks, Ted, for inviting me and for that very nice introduction. So I hope you had a chance in the meantime to read my abstract. And so I want to start with this famous quote by Steve Weinberg, saying like, if the reader is mystified at what Heisenberg was doing, he or she is not alone. I have tried several times to read the paper that Heisenberg wrote on returning from Helgoland, right, where he went to seek relief from an attack of hay fever, and the story is that he came up with matrix mechanics there. And Weinberg says with false modesty, although I think I understand quantum mechanics, I have never understood Heisenberg's motivations for the mathematical steps in that paper. Now, there's a very nice paper that I can highly recommend by Aitchison et al. That fill in these steps, right? So like understanding Heisenberg's magical paper, a new look at the calculational details. And so for magical, you need to like look at the rest of this quote where he says like, theoretical physicists in their most successful work are either sages or magicians. It's usually not difficult to understand the paper of the sages, but the papers of the magicians are often incomprehensible. Heisenberg's 1925 paper was pure magic. Okay, that's where the quote comes from. Now note, to go back to the earlier part, that Weinberg doesn't say that he doesn't understand the calculational details, he doesn't understand the motivations for them, okay? And so, this is the plug for my book with Tony Duncan. If you want to understand both the mathematical details and like the motivations behind them, look at our book. Like here is the relevant chapters, and we also have like a web resource where we deal in great detail with like dispersion theory. And so the basic idea is that like the reason that Weinberg was puzzled is similar to the puzzlement that you have when you come upon an arch and you wonder, how did that get there? And the reason you're puzzled is that the scaffold that was used to erect the arch is just no longer there, right? That's the basic That's the basic idea. And as Ted was indicating, that's also the metaphor that we use for the book. So here's the book. I brought copies. You know, I'll pass them around. I mean, like they're so thick that they tripped the security at Minneapolis airport. I'm not kidding you. They actually looked inside to see whether there was something hiding in the books. So I'm not going to cover the books, but you know, I will talk about what I want to do is you're not going to walk out of here with like an understanding of this famous like Umdeutung paper, but I hope you will understand sort of the very different ideas that fed into this that have now completely fallen by the wayside. Now, so I recommend you read the book. The other thing I highly recommend is that you get a copy of this book, Dover. Maybe many of you have the Sources of Quantum Mechanics by Van der Waarde. Just about all the papers I'm going to be talking about are collected in this book in an English translation with a very nice introduction. The only downside of the introduction is that some letters are quoted in German, but by now Google Translate is so good that you can easily get like very serviceable translations into German. All right, so the background image that you're looking at is a drawing of like a cartoonist that I've been working with, like Laurent Todin, and it's his version of like a print of the construction of the Strand Bridge, later renamed the Waterloo Bridge over the Thames in London. Right? So this is the idea of like the arch of the scaffold. So here's the outline of my talk, right? So this story about how we got from the Kramers dispersion theory to matrix mechanics is like, you know, a prime example of what we mean by like, you know, arches and scaffolds. So here's the outline. So I'll talk a little bit about the classical dispersion theory, attempts by Sommerfeld and de Baeye to adapt the classical theory to the new theory of Bohr. It's a failure. Then the first more successful theory of dispersion in the context of quantum theory by Ladenburg and Reiche in the early 20s. Then, you know, since I'm the physics colloquium, I felt I should give you at least some calculations. So I'm going to do two calculations for you. The first is the derivation of the Kramers dispersion formula. And then, you know, like I'll show you how this Kramers dispersion formula did scaffold this Umdeutung paper as sort of a first pass. I'll say very little about the completion of the arch, right? This, as I've mentioned in the abstract, even though this initial paper by Heisenberg is very mysterious, the follow-up papers by Born and Jordan and the famous Dreimännerarbeit of Born, Heisenberg and Jordan, I mean, those are very accessible to if you've taken a class on quantum mechanics. There's a lot of textbook results that you will recognize in that. But I'll backtrack a little bit because I want to look at sort of another road that leads into the Umdeutung paper, and that is like the infamous Bohr-Kramers-Slater or BKS theory that flared up and died quickly like in 2025. And so I'll show how that also, like, you know, was important for in Heisenberg's thinking to come up with the theory. But I'll argue that the sense in which it was important was almost entirely through dispersion theory. So in many ways, this BKS theory was a bit of a sideshow. But like it's important, like for the historical understanding, like, you know, what was up with that. And so then finally, like I'll do the second calculation, like in unabashedly like modern terms, namely to show you how you get from the Kramers dispersion formula to, you know, the core of the new quantum mechanics, like in the hands of Born, Heisenberg, and Jordan, namely the commutation relation for position and momentum, and that goes through another result that is directly related to dispersion theory, namely the Thomas-Kuhn sum rule. Right? And so this is specifically for Ted, who has been asking me about the Thomas-Kuhn sum rule. And so this is at least sort of a modern calculation. If you want to see like the calculation in its full glory in the original version, like, you know, read the book. And so I'll wrap up talking about like the development of quantum conditions in the first quarter of the century. All right, so now dispersion, of course, has a long history. going back to at least to, you know, like Descartes' rainbows and Newton's prisms. But the first satisfactory theory of dispersion dates actually from the late 19th century. And the phenomenon that was particularly difficult to account for is what became known as anomalous dispersion, namely that in some frequency ranges, the index of refraction goes down rather than up, you know, with frequency. So this was discovered in the 1840s by early pioneers in photography and was studied more seriously in the 1870s. And so, this guy in particular, like Walter Sellmeier, like proposed like, you know, one of these theories that was then picked up by Helmholtz. And basically, like, you know, what they realized was that anomalous dispersion calls for a theory that involves like resonators, like inside like these transparent media. And so initially it was done purely in mechanical terms, and then, you know, with the acceptance of Maxwell's theory in the 1890s, it was like redone like now in terms of electromagnetism. Right? It's done by Lorentz, Helmholtz himself, and by Druden. And so basically, like, you know, to fix the idea, right? So you have like frequency of external radiation of driving frequency nu hitting a charged oscillator with like resonance frequency nu naught, right? So you can picture it like this. And the idea is that, you know, this driving frequency gets superimposed on like the oscillation of this oscillator. And like the amplitude of that additional oscillation, like, you know, gets bigger if the driving frequency gets closer to the resonance frequency, and you get absorption when, you know, like these two are equal. And so it's this additional oscillation that produced like, sort of the secondary radiation that we witness as refracted radiation, like, you know, this sort of the coherent scattering. So again, to fix some terminology, right? So we have like we have an E field with I'm sure I should put here, like, you know, with some angular frequency omega naught, or ordinary frequency nu naught, you know, like charge mass m, charge minus e, spring constant k, all the usual stuff. If there's no field, right, the solution is simply something like that. If there is a field, right, you make the ansatz that it looks like something like this, that you have this, you know, coherent displacement. You assume that that's of this form. If you stick that into Newton's second law, you find that the solution for this amplitude is this here, where you see that this thing has a pole. Okay? And so the polarization that is determining the index of refraction is just multiplying this coherent displacement by the charge, like minus E, and you get this expression. Okay? Now, to get a sense of what that looks like, right? So, you know, you see that the polarization is proportional to this expression. It's also proportional to the index of refraction squared minus 1. You know, just put like an equality sign there. We're only interested in sort of getting a sense of, like, you know, what this looks like, and then you get like a graph like this, where you have, like, as long as you ignore absorption, you get, like, you know, the pole over here, right, at this point. If you now put in absorption, and again, like, if you, in the gory details of this are all in this web resource for the book, it tamed it a little bit, and you get this, and now you actually do explain anomalous dispersion, because you see that in this frequency range, the frequency indeed does go down. But that's the basic idea of this theory. And, like, you know, of course, you now want to extend this to not just like one resonance frequency, but a whole bunch of them that you identify with the absorption frequencies of the material. So you get like something like this. And so this is sort of a toy example where you have two resonance frequencies, and like and then the idea is that this Fi, which is known as the oscillator strength, in this theory is just the number of dispersion electrons with that particular resonance frequency, right? So this is and the pole, it has poles for like all the resonance frequencies, and this is just a toy example, right? So where you just have like 6 of these dispersion electrons, like 2 with frequency 1 and 4 with frequency 2. Beautiful. All right, so 2 centuries after Newton, there was finally sort of a semi-respectable theory of dispersion. Unfortunately, just 2 decades later, like Bohr yanked the ground out from under it, because instead of this kind of picture, this of course is my drawing, but that was the picture that people had. Now it gets replaced by this picture where now the electrons are orbiting the nucleus. Okay? Well, not to worry, Sommerfeld and de Baeye set out to now adapt this theory to the new situation, right? So before we had the wave coming over this. Well, we can also now just replace this by something like that, right? So this would be the equivalent for my toy model: 2 electrons with frequency 1, 4 with frequency 2, and you have the thing coming over it, and the idea is the formula just stays exactly the same, and the only thing that changes is that I went a little too fast here. The only thing that changes is that instead of talking about oscillation frequencies, you're now talking about orbital frequencies. Unfortunately, that theory is completely untenable, right? Because you get the poles at the wrong frequency. And because clearly what this Sommerfeld-de Baeye theory predicts is that the poles are going to be at the orbital frequencies. And the problem with the Bohr atomic model is that the orbital frequencies and the absorption frequencies are not the same. It's only in the limit of high quantum numbers that these orbital frequencies become the same as the transition frequencies. Right? This was actually seen at the time as the most radical step in the Bohr atom, right? And just to show you that, here is Planck in his Nobel lecture. He says that in the atom, certain quantized orbits should play a special role, could well be granted. Somewhat less easy to accept is the further assumption that the electrons moving on these curvilinear orbits radiate no energy, but that the sharply defined frequency of an emitted light quantum should be different from the frequency of the emitting electron would be regarded by a theoretician who had grown up in the classical school as monstrous and almost inconceivable. Okay? So now Bohr, to his credit, realized early on that this was a problem. Okay? I cut out a few lengthy quotes by Bohr where he says this. But he didn't know what to do about it, right? So there was plenty of other problems to worry about, so they just let it sit. Now, what actually sort of helped things along was that the classical theory also turned out to be untenable. And there, the problem was not, as for the quantum theory, the problem is in the denominator. For the classical theory, the problem is in the numerator. Remember, I talked about these FIs, right, the oscillation strength. And so basically, these are parameters that you fit to the data. And in some cases, the best fit would give very low values of this. You would have 1 dispersion electron of a particular resonance frequency per 50,000 atoms. That clearly goes right against the picture I showed you, where the idea is every atom has on the order of 1 or 2 of these resonators for these resonance frequencies. So what was going on here? So this problem was solved by Ladenburg in 21, and in collaboration with Reiche, further developed. Ladenburg was experimentalist, Reiche the theorist. And so what they did is they reinterpreted this oscillator strength. So before it was the number of dispersion electrons. In their theory, it becomes the number of transitions, okay? And so they focused on the ground state. So the number of transitions from some excited state to the ground state, and so that would be equal to the number of electrons that are in the excited state times the probability that they're going to make a transition to the ground state. And for that, they used the Einstein A and B coefficients from Einstein's 1916, 1917 work. As an aside, I think that paper of 1917 was much more important for the development of quantum theory than his paper on the light quantum in 1905. So, all right, and now, of course, the numbers could be much lower, right? Because the occupation number is low, there's the probability, so that would do it. And so Ladenburg and Reiche, they talked to Bohr about this, and in a special issue of Die Naturwissenschaften, to celebrate the 10 years of the Bohr atom, they say we have to admit that we do not know the true mechanism through which an incident wave acts on the atoms. We nevertheless believe, on the grounds of the observed phenomena, that the end result of a process in which a wave of frequency nu acts upon the atom should not be seen as fundamentally different from the effect that such a wave exerts on classical oscillators. And so they then introduce like the idea of Ersatzoscillatoren, substitute oscillators, as sort of a placeholder for this mechanism of dispersion. This was suggested to them by Bohr. All right, now, so Bohr is interested in this problem. He gets his right-hand man, the Dutch physicist Hans Kramers, to look at this. And so he makes the next step, right? So remember where we are. So we went from this, we went from this classical formula to, you know, replacing this by like, instead of just numbers, you have these transitions. Instead of like the orbital frequencies, you put in the transition frequencies, and you get this formula. Now, it has two limitations. A, like it's only, as I mentioned, it only holds for the ground state. And B, I haven't really said anything about replacing orbital frequencies by transition frequencies. They just did that because they knew that that was unambiguously what the data were telling them. There's no theoretical justification for this. So this is where Kramers comes in. So Kramers comes up with an argument based on the correspondence principle that I'll explain to you, that you know, the formula should be like this, and so it gets rid of both these limitations. So there's a correspondence principle argument for replacing orbital frequencies by transition frequencies, and like there's no longer, this thing is no longer restricted to just the ground state, it could be any state. Right? So this is what the formula looks like. And now, the problem for historians is that Kramers was very slow in publishing that formula. Right? So he found it somewhere in the fall of 1923, but it's not till like, you know, like 24 July that he puts like short notes in Nature that really don't give the derivation, and it's really only in early 1925 in a paper co-authored with Heisenberg, that will become important, that he works this out. And this causes problems both for physicists working in this area at the time and for historians like me trying to reconstruct what happened. And so, for instance, like both John van Vleck, much more on him later, and Max Born, they both published derivations of this Kramers dispersion formula before Kramers himself had. And van Vleck actually wrote to Kramers apologizing, and Kramers said, well, don't worry about it, right? I mean, like, I haven't got around to this. And so the other problem is that Kramers, when he finally got around to publishing it, he published it in the context of this controversial new theory, the Bohr-Kramers-Slater theory, where it's like, you know, he clearly had found it before, right? But the BKS paper was published before Kramers published this paper, right? And so that leads to confusion because this BKS theory would just be decisively refuted like a year later, but it doesn't affect like the Kramers dispersion theory at all. So here's the evidence that Kramers had this earlier. This is actually a pretty amusing letter from Slater to his Harvard classmate, Harvard, after he was at Copenhagen for a bit. And so he says, well, don't remember just how much I told you about my stay in Copenhagen. The paper with Bohr and Kramers was got out of the way the first 6 weeks or so. That was very nearly the only paper that came from the Institute at all the time I was there. There seemed to be very little doing. This is my favorite line. Bohr does very little and is chronically overworked by it. Kramers hasn't got much done either. You perhaps noticed the letter to Nature on dispersion, the formula, and that he had when I came, right? That's the smoking gun. Although he didn't see the exact application. Except for that, he hasn't done anything so far as I know. They seem to have too much administrative work to do. Even at that, I don't see what they do all the time. Bohr hasn't been teaching at all. Kramers has been given 1 or 2 courses, right? So a rather unflattering portrait of, like, you know, the great institute in Copenhagen. So I want to walk you through van Vleck's derivation of the formula. So van Vleck is one of my heroes. Van Vleck he did this while he was on the faculty of the University of Minnesota, and I've actually named my cat after John van Vleck. Like, as you can tell from my accent, I'm originally from the Netherlands, and Vlek is the Dutch word for spot, right? So it's appropriate that And so this is a picture of my cat when he was younger. And you can see that, like his tag has like, Professor John H. Van Vleck. I got rid of that because like I figured if they find him, they think which idiot is going to put not only his name on the tag of his cap, but also puts down that he's a professor of sorts. So now it just says Vleck on this tag. Anyways, so now Van Vleck recalled like later that he actually gave a talk in Minnesota while Ehrenfest was visiting. So Ehrenfest wanted some faculty member to give a talk while he was there. And so then I'll read you the last part of the quote. So he says, I remember Ehrenfest being surprised at my being so young a man. The lengthy formulas for perturbed orbits had given him the image of a venerable astronomer making calculations in celestial mechanics. Okay? And so from the calculation to which I'm going to subject you, but I'll go fast, you'll see why Ehrenfest had that reaction. Okay. So before I give you the gory details, let me just give you like the outline of how this works, right? And so basically the idea is, and I'll say a little bit more about this, is that you describe the Bohr orbits in very special like position and momentum coordinates known as action angle variables, and you use like the action variables to impose the quantum conditions, like this. So this is the Bohr-Sommerfeld quantum condition. Now you use techniques from classical mechanics to derive like a classical dispersion formula. And the result is a derivative with respect to these action variables of some expression that has like frequencies and amplitudes of the Fourier expansion of the motion. Okay? Now you invoke the correspondence principle, which by 1924 has taken this rather sophisticated form that you need to make 3 substitutions to get from a classical to a quantum formula. So first of all, you replace like or orbital frequency by radiation frequencies, right? And the justification is that in the limit of high quantum numbers, these things are going to merge. So if you do this substitution, you're guaranteed to construct like a quantum formula that merges with the classical one, like for high quantum numbers, and then you just take the leap of faith that that formula will continue to hold all the way down to low quantum numbers. That's the strategy. So instead of the amplitudes squared, right, for the intensities, you have like transition probabilities, right? This was the idea of Ladenburg and Reiche. And here is the new idea of Kramers that was independently discovered by Born and Van Vleck. It's often called the Born rule, not to be confused with the Born probability rule, but the Born rule. But it's really like, found by these guys independently. And that is that in the limit of high quantum numbers, you can actually replace derivatives by a difference quotient. Okay? And so this also explains why you had the 2 terms in that formula. All right, so now the ugly calculation. I'm going to go fast. I just want to give you sort of an impression of how this goes. You can read the gory details in the papers. So you need to calculate like the polarization of some multiply periodic system. And I'm going to just do this for a simple harmonic oscillator. That's going to be messy enough. And you're going to do this in canonical perturbation theory and action angle variables. Now, of course, if I do this for the harmonic oscillator, this is really like using a sledgehammer to crack a nut, right? We just did that calculation. But Van Vleck explains, he says, look, if we were to study that just using Newton's second law, it would be impossible to make further progress without specializing the form of the potential function. However, it is quite a different story when we compute the perturbation in angle variables W1, W2, W3, and their conjugate momentum. In fact, by using them, the periodic properties of the system come to light even without knowing the form of the potential. Right? And it was, of course, in that context that these variables were introduced in celestial mechanics. So the strategy then is to assume that you can solve the unperturbed system in action angle variables, and you then calculate the perturbed system in those very action angle variables for that unperturbed Hamiltonian. This is where Van Vleck's calculation is different from Born's, because Born is trying to find action angle variables for the full Hamiltonian. That remark will hopefully become clearer in a minute. And again, I'll focus on the simple harmonic oscillator. I just want to give you the flavor of how this works. Okay? So here is as a quick reminder, action angle variables. So basically they're special variables such that the Hamilton equation takes a very simple form, namely that the Hamiltonian is going to be independent of the W, right? So it just depends on the action variables, right? Where like the frequency here that you get is some characteristic frequency of the system. And they were introduced in celestial mechanics. And the idea is that you solve the problem by finding a contact transformation to these action angle variables, and then you would learn immediately about like the periodic properties that you're interested in without having to solve the entire problem. Now, they were introduced into quantum mechanics, interestingly, by an astronomer, namely Schwarzschild. So Sommerfeld had already introduced these quantum conditions, like just the integral PdQ. And Schwarzschild pointed out to him that these are just like action angle variables, like long familiar to astronomers. Sommerfeld, who was like more sophisticated mathematically than most physicists at the time, wrote to Schwarzschild like, "Oh, I had no idea." Right? And so then like people really started to like bone up on this. So Schwarzschild says, "Look, before I made that connection, that way of quantizing wasn't looking very convincing to me, but now I'm all sold." And so he's saying, like, there are violins hanging all over the quantum heavens, where Schwarzschild would die very shortly thereafter, so he would not reap the benefits of this himself. And so, this whole complex of, like, comes from, like, Hamilton-Jacobi theory. As Tony Duncan likes to say, like, learning Hamilton-Jacobi theory is a bit like quitting smoking. I've done it many times. And so this was highly relevant for like about 10 years, and of course, like given inertia being what it is in teaching, it is still festooning like graduate textbooks in classical mechanics, though I understand most people don't actually cover those chapters. All right. Now, so this is what Van Vleck is going to do. And so again, this is the Hamiltonian for the harmonic oscillator with the perturbing field. And recall that, the elementary calculation, we already had this, right? That should come out. So what are you going to do? Right, so the details are in this paper and in the book. So you're going to look at, all right, so what is this displacement in action angle variable? So you write a Fourier expansion for the simple harmonic oscillator. It's going to look like this, right? So there's just going to be two terms. And by imposing this condition, you make sure that this thing is real, right? Of course, like in general, so Van Vleck does this for a generally like multiply periodic system. It's sort of pairwise that this condition is making sure that that this is going to be real. All right, so now you get to work, and you stick it in, and now you're going to look at, well, what's the change in this in the action variable? Well, you integrate the change in the time derivative, because the time derivative you know, like from Hamilton's equation. And so you put this in, and you now get this result, right? Now you put in, for the cosines, you're going to write these like in exponentials. You use that, like since it's only to first order in the field here, that to first order this W is just the frequency of the unperturbed system, times T. You put that all in, you get this, right? And so now you integrate that, and you get this horrible looking expression. And so, as usual, things get worse before they get better. Same for delta W, right? Same trick. Change in the time derivative. Like now you integrate that. And you get this, and now once again you integrate that, and so now you have both delta W and delta J, and you stick it into that equation, and you get this horrible looking thing where I've only written out half of it. You get another term if you replace it, right? You can see why Ehrenfest was saying you reminded me of like a venerable astronomer. All right. Now, fortunately, we're only interested in part of this, remember, because we're interested in coherent scattering. So we're only interested in the bit of this that varies with the driving frequency nu. And as you can see, those are the terms where tau is equal to minus tau prime. Right? So that double sum, like, reduces to one sum. It looks like this. Now it's getting a little bit better. So now I can write it out again instead of just having this here. I see that this here just reduces to that. And of course, this thing is real, right? We guaranteed that. You can check that because the imaginary part is indeed going to be vanishing, right? And so what you're left with is the real part with the cosine. And so you can also, like, simplify this. You see now there's tau squared and tau squared, so these tau plus or minus 1 are just the same. So you just, instead of the sum, you just get an extra factor of 2, right? So that would be this. And so now we're almost there. So this bit I didn't explain to you, but like from the analysis of the unperturbed system, you can find a relation between these amplitudes and the action variables. You stick that in, and now, lo and behold, you have, like, the equation that we had in 3 lines, like in just doing F equals ma. Right? So what have we gained? Well, what we've gained is that now you have like a way of translating this thing into a quantum formula. Right? So I'm going to cheat here a little bit. I'm going to put the frequency inside this here. Now for the oscillator, it doesn't matter because the frequency is not dependent on J, but this is a subtlety like in the real calculation where you have to be very careful about this because then mu is going to be dependent on J, but you do get this result. Okay, so now you do what I sketched before. I showed it in a little more detail. So you do this, the correspondence principle, you're going to replace orbital frequencies by radiation frequencies. Right? Of course, for the harmonic oscillator, that's trivial because like all these frequencies are the same. It's just the idea here. You replace the amplitudes by transition probabilities, derivatives by difference quotients, and so this is the recipe. And so following Ladenburg, this is the concrete form of replacing like squares of Fourier amplitudes by transition probabilities. Then you use this rule of Kramers and Van Vleck to change this derivative into a difference quotient. Right? So plugging all of this in, you get that. So that reduces to this. And then finally, you do this. You replace the orbital frequencies by the radiation frequency, and you get this. And this is the Kramers dispersion formula for the simple case of a simple harmonic oscillator. And you see, like already how much. Like work needs to be done just to do this for the simple case. Now, all right. So from that to the, to the polarization for like in 3 dimensions is all fairly straightforward. The important thing is that if you look at these formulas, you see that the only thing that occurs in there are transition frequencies and transition probabilities. And all reference to individual orbits has dropped out of this equation. Okay? That is key to Heisenberg's Umdeutung paper. Remember, Heisenberg co-authored a paper with Kramers, like going through all of this and doing way more complicated calculations than the ones I just showed you. They're also looking at incoherent scattering, getting the Raman effect and all this. So Heisenberg knew this backwards and forwards. And that feeds into like his famous paper on Umdeutung. And the basic idea is simply this, that he applies that translation scheme of Kramers in a clever new way. What Kramers did was that, as I showed you, he did the entire calculation classically, and he translated the end result into this quantum formula. The basic idea of like Heisenberg is to just do the translation right at the beginning. Okay, so instead of like starting from where I started from this this Fourier expansion, he is going to just say, okay, we're going to translate this, and now you get this matrix, right? As we would now call it. Like, of course, he didn't know about matrices, so it's like some sets of numbers, and we're going to calculate in that. And so he also realized that, look, that strategy in principle should apply not just to dispersion, but you should be able to compute any problem that you care to do this, right? So the slogan that I like for and why it's called Umdeutung is, we're not going to repeal the classical equations. No, we're going to reinterpret them by, instead of having like these numbers related by the equation, we have like arrays of numbers, right? Which turn out to be like that turns out to satisfy like a non-commuting multiplication rule. Again, that has its roots in the Kramers-Heisenberg paper, but it would take me too far afield to go into that. Now, So a little bit of the sort of the romance that has grown up around this, because as I mentioned, as Weinberg mentioned, Heisenberg supposedly did all this on Helgoland. And so, this is from his book, Der Teil und das Ganze. In the English, I don't know why, it was not published under the Part and the Whole, but it's called Physics and Beyond. So he says, I was ready to determine the individual terms in the energy table, or as we put it today, in the energy matrix. It was almost 3 o'clock in the morning before the final result lay before me. I was too excited to sleep, and so as a new day dawned, I made for the southern tip of the island where I'd been longing to climb a rock jutting out into the sea. I now did so without too much trouble and waited for the sun to rise. Okay? I mean, there's sort of this romantic view, and he comes back, and I'm sure, in the year after quantum, you're going to hear versions of the story, he came, so the basic idea of the story is that, matrix mechanics emerged fully formed, like Athena from the head of Zeus, from Heisenberg's runny nose on Helgoland. Okay? And so my cartoonist has tried to, capture that idea. That, of course, is nonsense. Okay? And so, as I put in the abstract, right, so Landé was not entirely wrong. In part, it was sour grapes, because Landé sort of missed the boat, right? He was a prominent theoretician who sort of did not make the breakthrough to quantum mechanics. And so he told, Kuhn, he says, well, Heisenberg stammered something and Born made sense of it. Okay? And so, yes, that's to a very large extent, this is true, that, it was in Born, Heisenberg and Jordan, that they recognized sort of the structure that was hidden in this very sort of dispersion theory informed product that Heisenberg had produced. All right, so I don't want to go there. I want to look at the road to Umdeutung, right? And so Max Dresden, the biographer of Kramers, of course, he is a bit biased. He is on record in his biography of Kramers. He says the Kramers-Heisenberg paper is the direct, immediate, and exclusive precursor to the Heisenberg paper on matrix mechanics, right? And he then speculates that if Kramers had not allowed Heisenberg to add his name as a co-author, that maybe Kramers would have shared the Nobel Prize for matrix mechanics with Heisenberg, because this was a critical piece leading up to it. All right, now more recently, my colleagues at the Max Planck Institute for History of Science in Berlin have argued, and I think plausibly so, that in fact, another line that went into this that I don't cover here, but it's covered in the book, namely Heisenberg worrying about intensities of of fine structure lines, that multiplet lines, that was as important or even more important in formulating. Right? So this is what historians are still bickering about. Now, I don't want to look at this. I want to look at this other strand, as I mentioned, the Bohr-Kramers-Slater theory, and argue that once again, this is part of this dispersion theory influence. And so this is some, you're going to get into some nuttier stuff, right? But I think it's important to recognize that this is what what these people were thinking about at the time. And as a historian, I don't just want to sanitize what people were doing. So right, so this is what Slater was talking about to Van Vleck. And so this is the paper, quantum theory of radiation, famously has only one equation, the Bohr frequency condition. And so Slater, looking back on this, he says, I propose the existence of waves to guide the photon, right? A rather obvious idea which occurred to many people, but here's the important part, but I included the unfamiliar suggestion that the electromagnetic waves forming the light should be emitted or absorbed during the stationary state rather than just at the time of the quantum transitions, right? And then he gives some argument about, you need to understand that, from just the Fourier analysis of the lifetimes of spectral lines. And so he recalls, when I went to Copenhagen, Kramers and Bohr liked part of it, but they really objected to this idea that you would have like quanta, right? I mean, Bohr was dead set against like quanta, right? It goes very much against this idea of the correspondence principle that, in the end, it merges nicely with classical electrodynamics. So, Slater caved, right? And so they published this paper, right? And so again, like he said, well, the new suggestion was that, you know, it's the stationary state during which the atom is radiating or absorbing. Right? So it's a pretty radical change from what we know as the Bohr theory, right, where it's only when you have these transitions. And moreover, he says it's not just radiating like the frequency to which it's going to jump. No, it radiates all possible transition frequencies. And what does this radiation do? This radiation determines through an unspecified rule the probability that there's going to be these jumps like in another atom, right? And that means that you have to give up strict energy conservation. That energy conservation now becomes a statistical phenomenon if you average over many of these events. Okay? And so the same thing is, this is more like, you know, to convince you that, you know, this is really what these people were saying. Kramers is saying like, yeah, this is actually very nice because that gets us closer to, like, you know, this correspondence idea of Bohr. So here's a concrete example. I'll go quickly. Right? So the idea is like, you know, like suppose like, you know, the electron is in orbit number 3. So that means that it's radiating like, you know, all these frequencies, like jumping to 2, 1, and up to higher orbits. And like, you know, there's another atom B that's like, you know, where the electron is in state number 2, like that absorbs this. And like, you know, the radiation of frequency like, you know, 3, 2, like determines the probability that this electron is going to jump to that orbit. Okay? And so clearly you can't do that. That is the end of strict energy conservation. Now, the other thing that's interesting about this is that you get sort of a dual representation of the system. So you have, like, you know, as before, you have these orbits, but now you have what Landé called like an orchestra of virtual oscillators. And these virtual oscillators, as BKS makes very clear, are just these substitute oscillators of Ladenburg and Reiche that I was talking about in dispersion theory under a new name. Okay? And so in addition to these orbits, there's now you need to look at, okay, where can the electron jump? And for every jump, there's going to be an oscillator. Again, this is my picture, but this was the way they were thinking about this at the time, right? So this is for orbit number 1. For orbit number 2, there's, you know, you can jump to the lower one or higher, right? So you have 3 more. For orbit number 3, like, you know, so you have a whole bunch of these virtual oscillators, an orchestra of virtual oscillators. Now, what's interesting is that Landé, like, introduced this term not for BKS, but for matrix mechanics. Because in matrix mechanics, they're also, like, you know, Heisenberg is talking about, you know, like these transition quantities, but he's never telling you what is actually transitioning between. Like, you know, the whole idea of a quantum state is not part of the original matrix mechanics, right? That would be supplanted later, you know, be it Schrödinger wave function or, like, you know, von Neumann, you know, vectors in the Hilbert space. So this is a placeholder. And that actually had a long afterlife. Like in popular books in Germany in the 30s, people are still talking about matrix mechanics in terms of like, well, you should think of it as sort of an orchestra of virtual oscillators. Now, Bohr used this idea of this double representation to weasel out of the evidence coming from the Compton effect that that light is like a particle, like the light quantum hypothesis. I'm going to go fast, you know the story, right? So now before, so, you know, most people saw this as definite evidence, right? Van Vleck, Sommerfeld, right? But Bohr was not convinced. And Bohr actually tried to resurrect an attempt by Compton himself to explain this effect in terms of a Doppler shift. And so here's the idea, here's the primary X-rays, that the electron is going to recoil and send out like secondary radiation, and you see that the frequency of that radiation goes down if you go to bigger and bigger scattering angles, right? Now, Compton rejected this because he found, like, okay, qualitatively that is nice, but quantitatively it doesn't work because the frequency, the velocity that you get for the recoil of the electron is not the same as the velocity that you need in order to get the right Doppler shift. So that's the end of that, right? Pretty convincing. Not for Bohr. Bohr thought, okay, I have 2 elements that I can play around with, the orbits of the electron and these virtual oscillators. And so, so he is saying, like, the electron itself moves with the recoil velocity. The oscillators move with the Doppler velocity, right? So this is like, and so they say in the paper, this is in the paper, so well, that in this case the virtual oscillator moves with a velocity different from that of the illuminated electrons themselves is certainly a feature strikingly unfamiliar to the classical conceptions. Okay? So, and they defend themselves like, well, in view of the fundamental departures from the classical space-time description involved in the very idea of virtual oscillators, it seems that the present state of science hardly justifiable to reject a formal interpretation as that under consideration as inadequate. This sentence has Bohr written all over it. You know, this is how he writes. Right? It's pretty nutty. So now this theory was, was refuted. So with variations on the Compton effect, you found that there is strict energy conservation in every single event. And so, Bohr, took it, was sort of resigned, and he wrote shortly after he was informed of these experiments, well, there's nothing else to do than to give our revolutionary efforts as honorable a funeral as possible. Okay? Einstein was relieved, right? You've all seen this quote that, Einstein had said earlier, like, well, if this comes to pass, I would rather have been like a shoemaker or an employee in a casino, than to be a physicist. Now, remember, Kramers and Heisenberg published a paper on Kramers dispersion theory before this theory was shut down. And in the abstract of the paper of Heisenberg and Kramers, they say that it's based on this BKS theory, and they say the conclusions, should they be confirmed, are thus supporting the BKS theory. Now here's another person who didn't like BKS, that's Wolfgang Pauli. So Pauli published a paper using some of these formulas from the Kramers-Heisenberg paper, but he says in a footnote, he said, like, these formula are independent of the special theoretical interpretation, independent of BKS. And he wrote actually to Kramers, he says, if I had not added that footnote, it would also have been true of my paper, that should the conclusions be confirmed, they would form an interesting support of this interpretation. That, of course, I had to counteract. This letter is actually pretty nasty. So he goes on to berate Kramers, saying, like, he calls like the BKS theory like a reactionary Copenhagen putsch, propagandized by you to fanatical excess. And like it's a magnificent stroke of luck that it's now come down, right? And for good measures, he says to Kramers, you should tell your wife, like every time you throw down all the curses of the Deuteronomy upon those who prefer freedom of thought over any kind of true faith, she shall sing to you merry tunes of spring, beauty, and love. Now, clearly, Pauli understands the difference between BKS and the Kramers formula, because later on, like a few months later, he wrote to Ralph Kronig, he said, many greetings to Kramers, whom I'm very fond of after all, especially when I think of his beautiful dispersion formula. Now, so despite the refutation of BKS, this idea of these virtual oscillators just survived, okay? And I may add that, never mind the Compton effect, these people working on dispersion theory, Kramers, Heisenberg, they just treat radiation as just a wave phenomenon, right? And they also are not bothered by the fact that, these virtual oscillators and like the physical systems they belong to don't stay in the same place. And so I won't read you the quotes in the interest of time, but Van Vleck, both before and after the demise of the BKS theory, is saying, like, look, these virtual oscillators, they are, it's artificial, but it is the only way to sort of make sense of this idea that the frequency are like the transition frequencies and not the orbital frequencies. Okay? So I want to say one thing that is interesting about this quote, namely, he talks about Slater's virtual oscillators. And this is sort of a confusion that is like present in the participants at this point. People have forgotten that these virtual oscillators, no, that was not what Slater introduced, right? Slater claimed credit for this idea that radiation occurs when an atom is in a stationary state and not during a transition. He never claimed credit for these virtual oscillators because that's just, the Ladenburg-Reiche substitute oscillators. This comes, again, straight from dispersion theory and is not specific to BKS. All right. So how does then this route through BKS feed into the Umdeutung paper? Well, the story would be very simple. Remember, you get this double representation, right? You have the orbits and you have the virtual oscillators. But all the physical information is in these virtual oscillators, right? The transition frequencies, the probabilities, like these orbits are just there for the ride, they don't do anything. So one way to proceed is to ditch the orbits. And there was already, like Pauli had been talking about this, like, that seems to be the problem with, like, we've taken over all this math from celestial mechanics, but we should not take over the picture of these orbits. Like Einstein realized that by 1916. So by the 20s, like, Pauli, drilling this into Heisenberg. So one way to understand what Heisenberg is doing is just ditch the orbits, go with the virtual oscillators, and write a theory in terms of those. And so other historians, like Edward McKinnon, has argued exactly that. The virtual oscillator model played an essential role in the process of reasoning that led Heisenberg to the development of quantum mechanics. And so now why, if you look at the Umdeutung paper, virtual oscillators are not mentioned with one word, but he has the plausible explanation that he did not want to say that because he knew he would catch hell from Pauli, who hated this whole virtualization of, right? You saw what he had to say about BKS. Now, if you don't want to take McKinnon's word for it, interestingly, like the Dutch physicist Casimir, that's also what he says. Like in his entry on Kramers in the Dictionary of Scientific Biography, a standard resource for historians of science, the notion of virtual oscillator was the starting point of Heisenberg's quantum mechanics. The virtual oscillators became the matrix elements of the coordinates. All right, now, so Heisenberg is asked about this, in interviews by Thomas Kuhn for the Archive for the History of Quantum Physics. And so, of course, you have to be very careful, like this is decades after the fact, but it's interesting. So Kuhn asking, for people doing oral history would immediately jump at this, like, you don't ask leading questions like this. But so Kuhn says, like, well, one transforms one's idea of the atom from a system of quantized orbits, I paraphrased that bit, into a collection of virtual oscillators that operate between states. And Heisenberg immediately takes the bait. Yes, that was it. This idea of an atom being a collection of oscillators was in some way contrary to the idea of an electron moving around the nucleus. Certainly this paper, BKS, prepared the way for this later idea that the assembly of oscillators is nothing but a matrix. But in this way, you can say that matrix mechanics was already contained in this paper. Right? But again, I'll point out that the idea of an atom being a collection of oscillators, that is not specific to BKS, right? That came from, once again, dispersion theory. So Kuhn goes on. He says, like, of Heisenberg, I had, of course, to think about the quantum condition. I could translate the Thomas Kuhn sum rule into what I call a quantum mechanical statement. I could see that this fixes the quantization. And so Kuhn says, well, using the Kuhn-Thomas rule, so like clearly he is uncomfortable referring to this as the Thomas Kuhn rule. So he's the only one I know that refers to this as the Kuhn-Thomas rule. is a stroke of genius, but one supposes that there were a lot of intermediate attempts. No, says Heisenberg, I would say it was rather trivial. I saw that if I write down the Bohr-Sommerfeld quantum condition and translate it according to the scheme of the dispersion theory, right, which is precisely this translation scheme that I showed you before, that then I get the Thomas Kuhn sum rule. Now, what is the Thomas Kuhn sum rule? The Thomas Kuhn sum rule is just the high frequency limit of the Kramers dispersion formula, right? So once again, like, the elements that Heisenberg here identifies as critical to the road to matrix mechanics, like with the asterisks that we're talking about, like 4 decades after the fact. All right, so is once again not BKS, but is dispersion theory. Now, I think in the interest of time, so I promised I would do one more calculation. What is the canonical stopping time? I see that it's 4 o'clock. We're there. So should I? Do you want me to quickly show you? I mean, this is a calculation that like is familiar ground. Okay, I see some people nodding, so I'll just go through this. I mean, like, and again, like you can read. I mean, I'm happy to share the slides with with TED, right? So you can post them and you can look at them at your leisure. So this is we do this in modern terms, right? And so I talked to Tony. It's like, yeah, it's okay to just do this. Like, it's more informative. And again, we do this for the harmonic oscillator. So, we do this in the interaction picture. So the first slide is just, reminding you of how the time dependence is carried by operators and states in the interaction picture, right? And how the evolution of states in the Schrödinger equation now turns into, after a few simple steps, into an equation where it just depends on the interaction bit of the Hamiltonian. So sadly, I realized that interaction here stands both interaction part of the Hamiltonian and the interaction picture. So that was less elegant. All right, so now you look at switching on the field. You get like this ket, right? This integral gives you how this changes. You introduce this ket r, where for t equals 0, the interaction picture and the Schrödinger picture are just the same. For the harmonic oscillator, you get this. The corresponding bra would be like that. And now you can actually start calculating the coherent displacement. Right? So you subtract, you take the expectation value at time t minus the expectation value at time 0. So you get this, you integrate, and so the parallel here, this is why we like to do this in the interaction picture, is that just as Van Vleck did this calculation in terms of action angle variables for the unperturbed Hamiltonian, here you do the interaction picture, right? You do it in terms of the eigenstates of the unperturbed Hamiltonian. So these calculations are very similar to each other. And this is part of why I want to show the calculation, because one of my more general points is that the quantum revolution, actually there's a lot more continuity in this transition from the old to the new theory than the standard sort of Kuhnian paradigm shift picture would lead you to believe. So you insert a complete set of states. So you now plow through this. Again, it gets worse before it gets better. But again, I'll trust me. So you work this out. You perform integrals very similar to the ones that you did before. Now once again you focus only on the coherent part, right? So a lot of this disappears, and now you're going to use a few insights. So first of all, when you see this difference here, that is the Bohr frequency condition. So you get this. You can simplify this a bit. The fact that it's real. Sorry for the typo. The fact that it's real, the signs here are going to cancel, and you get this dipole moment. And so now it's just a matter of writing the sum differently, splitting into we're talking about the system in some state R. To split the sum in states above and states below R, you get these two characteristic terms, and then you can actually identify these remember what Casimir was saying, these things here are related to these transition probabilities are related to these virtual oscillators. Now you get the expectation element, the matrix elements of position, and you get the Kramers dispersion formula. That was the hard part. Now it's very easy to see how this leads to Heisenberg's quantization rule. So you take the limit where omega is way bigger than any of these resonance frequencies, right? So this thing simplifies to that, okay? And that should be equal then, to the classical case, which is given by that. If you compare these two things, you get this very simple rule. This is, in modern notation, the Thomas-Kuhn sum rule. And so what was convincing for Heisenberg was that if he massaged that Bohr-Sommerfeld quantum condition using this translation scheme of dispersion theory, that he got this, right, which was a well-known consequence of the dispersion theory, right? So now the last step we need to do, right, again, that's only one page, is to recognize that buried in this is just the commutator. Okay? And so, we're going to combine the sums again and then split them up a little differently, right? Namely like that. And now, remember, like, Umdeutung, you keep the classical equations, you just reinterpret them. So we still have P equals mx dot, but these are now matrices. And you see that the matrix for the momentum is related to the matrix for position like this. So you can identify here and here, these are actually the momentum. And what you have here then is just the matrix element for the commutator. Okay? So this is, again, this is in modern notation. It's messier if you follow this through in the actual notation of the papers at the time, but conceptually this is what's going on. Okay? And so I want to end then by just showing you, the continuity of how all this came down, right? So like the earliest quantum conditions are by Planck and by Einstein, just setting epsilon equal to h nu or nh nu. Bohr, quantizes like angular momentum. Sommerfeld, like is able, and like a bunch of other people doing it at the same time, is able to sort of unify these two up to that point independent quantum conditions into this general one, namely like these phase integrals that then turn out to be related to action variables. And so then like Heisenberg takes that and turns it into the Thomas-Kuhn sum rule, and then like Bohr, Heisenberg, and Jordan produce like the commutator, and voila. Thank you. Yeah.
Was that commutator not in Heisenberg's original paper?
No, it's not. So, so Heisenberg, what is in the paper, which I glossed over, is Heisenberg is very aware that these sets of numbers, that if you multiply them, that they don't commute, right? But like he is unaware, he doesn't know anything about matrices. Neither did Pauli, apparently, with whom it is more surprising. But Born did. And so when now Born takes a look at this together with Jordan, they see, oh, this is matrix multiplication. And they are the ones who recognize that buried in this Thomas-Kuhn sum rule, which is the Heisenberg quantum condition, that's the only quantum condition that appears there, that those are the diagonal terms of the expectation value of the commutator, and then they prove that this is also true for the off-diagonal elements. So that's in the Born-Jordan paper, right? And so then like it gets repeated in the Dreimännerarbeit that Born and Jordan do together with Heisenberg. Yeah.
I just wanted to comment that not only was physics in an unusual state by modern standards at the time, so was medicine. So I was teaching quantum this semester, and I was looking up the history of matrix mechanics. And apparently before Heisenberg went to the island in order to deal with the state paper, he tried treating it with the standard treatment of aspirin and cocaine. So things have changed in the
That's where the late night formula derivations come from.
Which if I can give you like one more sort of recommendation, are people familiar with this book by Labatut, like when when we cease to understand the world? So there's like a lovely chapter devoted by Heisenberg on. I mean, like it's way over the top. But that's the most beautiful version of like the story that he did it all recovering from hay fever on Helgoland. Yeah. Okay. So did everybody hear the question? Okay. So yeah, I mean, so when I started working on this as a graduate student, I tried to read that Kramers Heisenberg paper. And I was completely baffled by this, so I showed you some of how messy that calculation is. But people writing on this saying well, this was par for the course, everybody at the time had no particular difficulties reading this, And so this is very true, but it is it's an interesting question because this is true for the part of the community that is connected to developments in Copenhagen and Munich, right? And they don't have to physically be there, right? I mean, Van Vleck was sitting in, of all places, Minneapolis, Minnesota. But that's sort of what they follow. Now, of course, in 26, a completely different version of quantum mechanics arrives on the scene, namely wave mechanics. And a lot of people, with a big sigh of relief, thank God we don't have to deal with this mess anymore. And so I was thinking about weaving it in, but there's a beautiful quote, we put it in a book by Schrödinger saying, oh, we now have this beautiful Hilbert mathematics, no longer all this mess from celestial mechanics. So it's a good point, but and I think it would be true today, right? I mean, if you're part of this community, you know this. And so the moment, remember I told you that even Sommerfeld tells Schwarzschild, I didn't know anything about this. Right? But then he immediately tells his postdoc, blocking on his name now, to start working on the Stark effect. Okay, and so this guy is immediately boning up on this celestial mechanics, and then barely gets the result out the same day as Schwarzschild. And from that point onwards, everybody is learning this because this is the tools. And so when I mentioned the wheels move slowly in teaching, so I'm sure you've all seen Goldstein's classic book on classical mechanics. If you look at the earlier editions of that, and you look at the footnotes and the chapters on Hamilton-Jacobi theory, canonical perturbation theory, he gives these texts from the 20s where this was explained for the use of people working at the frontier of quantum mechanics. And then in the second edition, some of these things disappear. And then, in the current edition with two other authors, it disappears completely. Epstein is the guy the student of Sommerfeld who figured out the Stark effect. Right? So it's sort of this community that has just boned up on what it now is very unfamiliar material, right? And so again, I do think that Steve Weinberg knew his Hamilton-Jacobi theory, okay? But so the bit that I think that Steve Weinberg was not seeing was the nuttier stuff that goes into this, because today, who is virtual oscillators, systems represented by mathematical structures that don't even stay in the same place. These kinds of things are very weird and have fallen by the wayside, right? So which is the thing I like about this arches and scaffold metaphor. It's not like I'm claiming that the thing is completely continuous, but it's you carefully build stuff on top of this, and then you can drop things out, when the new thing can stand on its own 2 feet. That's what it's appealing to me to that. Thank you for that question. Yeah.
So throughout the Colloquium, you mentioned 30 or 40 different names, probably.
Yeah.
Do you know if there were just pretty much those people working on this, or was there hundreds of people in the background?
That's a very good question. I don't. It's not hundreds. It's not hundreds. But my sense, and so I'm as you can probably tell from the way I talk about this stuff, I'm sort of what's by now sort of a rare breed in history of science, namely a conceptual historian. And so there are historians who are much more interested in these questions about communities and all this. So the best I can tell you is that early on, in 1900, 1911, right? So the period before the first Solvay conference, there it's really so I talk about Planck, Einstein, Ehrenfest, Nernst. It's really a very small cast, and everybody else is working on much more traditional things. Okay, then with the Bohr model in 1913, that is a game changer. All of a sudden, people are working on so before it was black body radiation, specific heats. It's really statistical mechanics of very simple systems. The only thing you had to quantize was a harmonic oscillator. Now the idea is like, oh, we can do this for hydrogen. Maybe we can extend, never got anywhere, but we can now extend this approach and understand like, more complicated atoms, molecules, like put them in electric and magnetic fields, see what happens there. And now like the community grows. It's still not, it's still not huge, but there are more, like I would say there is like, 3 times as many people, or not 10 times, but like, 5 times as many people as I mentioned, right? And like if you look at, a good way to do this would be just look at the index of the book. Right? So there's like, so for instance, I didn't mention anything about the spectroscopist. Again, like I'm also like focused very much on the development of theory. I mentioned Ladenburg as the experimentalist, but there's in Tübingen, for instance, like under Paschen, there's like a whole army, like there's a bunch of, I shouldn't say army, there's a bunch of people there, right, who are churning out the spectroscopic details that they immediately ship off to Munich, where like Sommerfeld is trying to make sense of this, like in the context of the theory. So it's a, does that answer your question? Yeah. Yeah.
What extent was Schrödinger?
I would say very little. Very little. Schrödinger like hated this stuff, right? He's on record saying this is repulsive. Repulsive. In print, in a footnote in one of the papers, he says this is repulsive, and he says like, I shudder at the thought that I would one day have to tell my students that this is the explanation of atomic spectra, right? So, and so of course Heisenberg returned the favor, saying like, that wave mechanics is disgusting. So they're real rivals, and so wave mechanics comes out of a very different tradition. And so like we also covered that in the book. I was telling Ted like earlier that I'm much more confident about the reconstruction that we've done of the development of matrix mechanics, right? Which again, like we give in much greater detail here. Mostly what I talked about today is what we did in the first, Tony and I, what we did in our first paper back in 2007. So much more confident about that than about the development of wave mechanics. But this much is clear, that comes out of sort of this earlier phase that I mentioned in response to the earlier question, where quantum mechanics was really about, the statistics of very simple systems, right? And so this, so this is like, like Bose comes in, right? And then this idea of de Broglie, that wave-particle duality extends to particles. It's those kinds of ingredients through Einstein's theory of the ideal gas that then, influence Schrödinger, and he wants nothing to do with this algebraic stuff that is going on the matrix side. So very quickly, so like in 26, right? Initially, like people are, so all of a sudden there's this embarrassment of riches, right? Because like, Ted was mentioning this earlier, like, this old quantum theory wasn't very successful at all. You could do very little with it. So initially, 1913, great excitement. 1915, Sommerfeld, great excitement. After 1916, it's just like, one failure after another. And so now all of a sudden there's the breakthrough, right? And then there's another breakthrough. And these theories seem to be completely different. Now, Schrödinger himself very quickly establishes that the theories are closely related to one another. And very often it's portrayed as like Schrödinger was the one who proved the equivalence of wave mechanics and matrix mechanics. That is, I don't think is true. Like he showed that they're connected. But very quickly, like very young John von Neumann, he does it, right? Showing that, look, the only difference is like, it's Hilbert space. And like matrix mechanics, like in modern terms, would be like, you talk about square summable sequences, and wave mechanics, you talk about square integrable functions. That's the difference, right? And it happened really fast. Like if you looked at the book, right? So this is like 1900 to 1923. This is 1923 to 1927, right? And I think that's about right. We could have been, less long-winded, but the things happen really, really fast. Now, so what I find fascinating is, so So in terms of, so I've become interested in sort of the pedagogy of this. So, you know, how is quantum mechanics being taught now, you know? And very quickly, this becomes a complete victory for the Schrödinger approach. Okay? So the only textbook that appears early on that has the matrix mechanics approach is a book by Born and Jordan, which, you know, produced one of the nastiest reviews ever in the history of physics by Wolfgang Pauli, where, you know, the famous last line, the only positive thing he has to say, the quality of the paper and the print is excellent. Okay? And he's saying things like, well, it's not because the grapes are hanging too high for me, because like I was the one who first figured out the hydrogen spectrum using matrix mechanics, but it's nuts to do that way once you have this much simpler wave mechanics. So wave mechanics, huge victory. All the textbooks, you know, are all like in wave mechanics. What I find fascinating is that with the rise of quantum computing, all of a sudden, you know, like these textbooks are saying, like, oh, you don't need to know anything about differential equations anymore. All you need to know is a smidgen of linear algebra, and you're off to the races, right? And that's much more sort of sympathetic to the Heisenberg approach. And so this, as a historian, that's given me, you know, I'm a historian in the physics department in Minnesota. As a historian, this has given me a new lease on life, because now all of a sudden it's actually interesting for physics students, physics majors, to learn that these two very different phases of quantum mechanics, like that you see in quantum computing, that you see in like everything else, like, you know, like not just atomic physics, but like solid state chemistry, that those two phases like, actually go right back to the founding fathers of the theory, and that they were bickering about this.
That's a good place to end. Thank you very much.
All right, thank you.